Oh, how's it going today? I had a viewer, actually not a viewer of my channel, but a curious person on another channel, where I kind of described something there in the comments, and it seemed that he didn't understand what I was talking about. So I figured I would make a video on that for him. And it's another, I've had in my life, I've had a few realizations about electronics. Some mathematical insights that I've kind of figured out just because I'm kind of curious about this stuff, and I never really stop asking questions. Um, and I've found some things, some mathematical connections in electronics and electrical engineering in general, that I feel I've never heard an electronics teacher say these things, and it really helped me a lot with my understanding. And I figured that I would share that. And this is actually one of those connections that I've kind of made. It's not really a discovery, but just I haven't seen very many teachers go into this sort of thing. Um, so what the comment I was talking about, it was on a video about capacitors, I believe, and their nature when it comes to their IV characteristic and how they present an AC impedance and subjects of that nature. So I wanted to describe what I was saying, and I'm an HVAC technician, so I actually use this equation out in the field quite a bit. I actually rearrange it and use it at work to test capacitors while they're under load. And there's a common equation that's been kind of simplified that other technicians use. Um, but the equation I use is actually the full one, and I'll explain because it can help you understand the way that capacitors behave far better than anything else. So with capacitors, so the granddaddy equation is I sub C. So that represents the current flowing to and from the plates of that capacitor. That value is equal to the capacitance of the capacitor times something called dV. We'll do d sub V divided by d sub T. And this is just a derivative here, um, that states that what this equation really says is that capacitor current is equal to its capacitance times the rate of change in voltage across the leads of that capacitor. It is actually the same as this. It's just that as the voltage rises across the capacitor, it rises at a slower and slower rate, which means the capacitor current goes down. And with direct current, once the capacitor reaches its full charge, the voltage is no longer changing. Therefore, we get zero as our IC value. So there's no capacitor current at that time whenever the capacitor is fully charged. Um, so right here, let's just say that we have a 5 microfarad capacitor. The power -6. What we'll do is I've never figured out how to do derivatives in Desmos. If one of you in the comments happens to know, let me know. But what we're gonna do here is we're just gonna do a poor man's derivative. So the way that we're gonna do that is let's imagine that we have an AC voltage. Um, and the way that you would describe an AC voltage would be like this. So you would say actually we would say V sine times 2 pi F. Now this 2 pi F many times gets shortened to uh, to a Greek letter omega. So you can also say omega here, but we'll just say 2 pi F. It's really no different. So 2 pi F times T. Now, in order to make this make more sense, what we're going to do is we're going to utilize the x-axis as our time axis. So we could put x here and have it work as a stand-in for time. All right. And the way that we're going to do this derivative, so a derivative in calculus simply tells you, say you have a sine function here, you know, it's going to tell you the rate of change. You basically choose a point in time, and the derivative will tell you the rate of change in that function at that time. So what we'll do is we can just say something like v sine 2 pi fx minus v sine 2 pi fx minus dt. All right, so this dt represents the amount of time that we are waiting to make a new measurement to determine the slope of the function. So what we need to do is we need to make dt equal something very small. That way, as you make dt smaller, the approximation of the derivative gets more and more accurate. So there we go is that. Now we need to give frequency a value. We'll just start with something like 3. That way it's easily visual. But in real life, the frequency is going to be a lot higher than 3. Um, and so, yeah, we need to add a V here as well. And V is going to represent the voltage across our capacitor, the amplitude of that voltage. And we should see here, we'll start to get a current flow. Now, um, you can notice something right off the bat here. Let's just go down here and we'll just make a normal sine function of 2 pi fx. You notice, let's make it the same amplitude as this one so we can look at their phase relationship. So 0.03. Yeah, so there's our phase relationship. So you notice any type of sine wave, any type of sine function has 3 parameters that can be passed to it. First one is the amplitude. That's what we just messed with. So as we change this amplitude and raise it or lower it, that changes the maximum height that the wave could be. All right. So let's try to get it close to what that one is. Um, so you notice here that if we were to take a derivative of this sine function, if we were to look at the slope of this red line at this dot at 0, it is pretty much the maximum that it can be. So that slope would look something like this. All right, but then what happens to the derivative as the voltage rises toward the peak? It gradually decreases, and eventually at this dot here, the peak, the derivative becomes 0. So you can see that here. The main question that I had with the impedance equation for capacitors, the impedance of a capacitor is equal to 1 over 2 pi FC at an angle of negative 90 degrees. And for me, I always wondered, hey, where does that 90 come from? Why is it not negative 180? Why is it not negative 45? Why does it have to be 90? And the answer is actually in this equation right here. It's in the granddaddy equation up here. So if you were to take the derivative of a sine function like we were just saying, the rate of change is greatest at 0, which means our current will peak at 0. And then, as the rate of change begins to fall, it falls to 0 at the peak. And so our derivative is 0 here. And so that means that basically the derivative of a sine function is the equivalent to an equivalent cosine function. And the only difference between sine and cosine really is that cosine begins at a peak and it at 90 degrees, the cosine of 90 is always 0. But the cos of 0 is always the peak. Now it's the opposite with the sine function. So at sine of 0, the sine of 0 equals 0, and the sine of 90 degrees is equal to the peak. So that's basically why. And so at work, the way that I check these capacitors, what I do is I rearrange this equation here in order to solve for capacitance. So if I wanted to solve for capacitance here, then I need to know the rate of change in voltage, and I also need to know current flowing to and from the capacitor. So you can do that by saying IC over dV over dt equals C. And that's what I really do at work to test these capacitors under load. So when I'm working, most of the capacitors that I'm troubleshooting are capacitors that are being used to create a phase change for a motor. So generally IC here is equal to the start winding current of the motor that the capacitor is attached to. So you can measure start winding current and divide it by dV over dt. And in order to find dV over dt, then I just do something like we described above. I look at the voltage over the capacitor or across it, and if it's 370 volts, then we can solve here. I'll actually demonstrate this for you. What we'll do is, we'll look at, say we have a condenser fan for for a for an air conditioner. Most of those take a 5 microfarad capacitor. And most of them, when they're functioning properly, they generally draw about zero point 0.7 amps, and the capacitor that's attached to them has about 370 volts across it. Now we need to change our frequency here. We'll change it to 60 hertz, because that is the power grid in North America here where I live. So now we have this. We have a frequency of 60. So that anytime you change this frequency, you've also changed the derivative of the function. So the derivative of a function is now significantly higher than it was before. But if we go up here, we could expect to see about 0.7 amps of current being drawn. And you can see here it comes up just a little bit short. So most of the time when I look at the start winding current of a condenser fan motor, and I see that it's about 0.68 volts, 0.69 volts, I know that the capacitor is likely okay. Now I still check it just to be safe, because if it's drawing 0.68 amps and it has 400 volts or more across it, that can indicate that the capacitor has lost capacitance and it's on its way out. You need to replace it. But likewise, yeah, this is basically the way that you would do that. Um, so IC equals C times dV over dt. Write that one on your heart. Don't forget it because it is very important and it describes everything about a capacitor. It doesn't matter if it's AC, DC, whatever, you know, that this equation will always be true for a capacitor, an ideal capacitor. Now I'll end the video here and I'll go to my phone and film something that could kind of flesh this out a little bit for you too if you're still having a hard time understanding. Um,
Okay, so on this breadboard here, I have a circuit that's called a curve tracer. And basically, it's a component tester that can tell you a lot of different things about a circuit. I made a video about it earlier if you're curious about that, but I'll demonstrate really quickly. So I have these two test probes right here, and this oscilloscope's just drawing a horizontal line right now. Now what's actually happening is the x-axis on this oscilloscope is no longer time. The x-axis of this scope is now being driven by this input, by this probe right here. So you can see if I remove it, it just goes to a dot. And what it's drawing right now is an AC voltage. So the beam is constantly moving from the center where the dot was out to this end at one peak, and then it's coming back, moving out to this end at another peak. Now, so the x or the y-axis now on the scope is drawing a current. So you can see I have an open probe, so there is no current flow because there's no path between these two test leads. But if I were to short them out right here, the line goes completely vertical. The reason why is that now, since we have a dead short, the voltage is no longer allowed to rise horizontally anymore. It can only rise vertically up and down because the circuit at this point is all current and no voltage. So close to zero impedance. Now, on the opposite case, if you have close to infinite impedance across the two leads, then you just get a horizontal line. And then resistors, they lie somewhere in between. So this 10K ohm resistor here would provide a slanted line to you. And then let's see here. I'll grab a potentiometer real quick, and we will rotate it and watch its resistance change in real time. Now this can clue you into a lot of bad audio components and things like that. So you can see here we got this potentiometer, and when we turn it, we get a rotating line here. So that potentiometer looks like it's actually pretty smooth. There's not a lot of noise being presented, so that looks really good. I have an older one that I pulled out of an old radio because it was crackling and popping. You can watch it on this thing and it looks horrible. There's just noise everywhere with it. So that is what a potentiometer looks like. But that brings us to the next thing. What would a capacitor look like in this device? And it obviously depends on the size of the capacitor. But let's just try it to see. This is a 0.33 microfarad capacitor here. Okay, so it still kind of looks like a line, doesn't it? But what happens if we adjust the gain? So we get an oval out of this. Now there's a lot of noise imposed on this. Real life capacitors are not perfect by any means. Electrolytics do generally tend to look a little better. So I have this electrolytic right here. It's 22 microfarad, which means that you'll see what this means here, and I'll explain. So this one is actually off of the screen. Let me turn this off so we can, not all the way. Let me plug this light in real quick. Turn this off so we can see a little better. So there, we get an oval out of it. Why an oval on this one? Let's turn the intensity down a little bit. So I'll kind of try to describe what's happening here. Let's widen it so we get a better look. Bring it center. So let's just make sure that we are centered on our line. Alright, so here's what's happening with this capacitor. So the impedance that this presents to the alternating current that's being given to it, if you were to measure this, there's about 9 volts of AC across this. That's why I have this little step-down transformer right there. So there's about 9 volts of AC across this. But what happens is a capacitor does not impede the flow of current linearly. There are times where it flows more current and times where it flows less current. And it was exactly the same as what I was just describing to you in Desmos there. So when you have, since IC equals C times dV over dt, when you have a sine wave that's being applied to this, it will draw the most current at the 0 point. And you remember when we removed this probe, the line is close to the middle, So when we remove that probe, that tells us that the 0 point on this scope, so the very center of that scope, is the middle of the sine wave. And so the outer edges are the peaks. So when you have 0, when you're in the middle of a sine function, that's when the derivative and therefore the current is the greatest. But then, as the voltage is rising this way, it begins changing less and less. And eventually, when you reach the point of the peak, there is 0 current being flowed into this capacitor. At which point, now, once we hit the 0 point here, this is when the polarity reverses. And so the electrons are moving the opposite direction, and therefore the current is as well. We get a discharge. So this would be like a discharge cycle on that capacitor. It is now providing current to the circuit, and the amount to which it can do that is dictated by that same equation. And so at zero, it's not going to flow any current. Then the voltage begins to drop across it, and it wants to provide current to prevent that from happening. And so you get this outward current here that peaks in the same fashion. It peaks where the sine wave is zero. And then it comes back and it comes full circle. So that is why a capacitor would draw an oval on that, and a resistor would just draw a linear line. So resistors are linear devices. The current flowing to them is just described by Ohm's law. Now capacitors, it still is described by Ohm's law, but it's a little more complicated. They do not flow the same amount of current all the time. That's why they call them a reactive component. Inductors and capacitors are reactive components, and we can check a transformer right here. Let's look at the primary side, because that will be the side that has the highest inductance value. And you can see as well, inductors are very similar to capacitors. They are reactive components as well. And the only difference is the current and voltage is flip-flopped. So that equation that I told you with inductors that states, IC equals C times dV over dt, the same equation applies to inductors, but the terms are swapped around. So with an inductor, it is VL, so the voltage across the inductor is equal to its inductance times di over dt. So they're very, very similar. In a lot of ways, capacitors and coils are mathematical mirror images of one another, if you will. But yeah, hopefully that clarified what I was talking about. There's a couple of other things I could go into if you would like, so just let me know in the comments. And thank you. Have a wonderful day, and good luck on your journey to enlightenment, your journey to electrical proficiency. Goodbye now.